The last type of two-mean test that we're going to take a look at is this hypothesis test of two means paired sample test. And before we talk about the mechanics and do a couple examples, I want to talk about when we would utilize a paired sample test. So generally, if we keep the same subject and we do a before and after or a comparison of that nature, then we're able to do a paired sample test. And let me give you an example of such a situation. For instance, let's say we wanted to test free recall before and after some sort of mnemonic technique. So let's say there's three people. So let's call them person 1, person 2, and person 3. And let's say that they're given a list of 20 items to recall. All right? And 20 different items each time. And let's say for some reason that they're just given it without any techniques of memorization. So let's just say without techniques. And let's say we gave them 20 items, and let's say person 1, let's say they recalled 10 of those 20 items. Let's say person 2 recalled maybe 8 of those items, and then person 3 recalled 9 of those items. Now let's say, for instance, that there was some sort of technique to be able to memorize rote objects, such as a loci method or a grouping method or something like that, to where you can more easily affix it with other connectors in the brain. So let's say they were taught that and they were retested and they were given 20 more. Okay, so this time they have these techniques. So let's say person 1 was able to memorize 13, person 2 is now able to memorize 9, and then person 3 was able to memorize 10. Now clearly there was an increase. But of course the question is always, is there a significant increase? All right, and that's what we're looking at. So we have a paired sample. In other words, this is a pair, and then we have another pair, and then we have another pair. Okay, similar to when we did scatter plots and bivariate data. All right, although it's going to be a different type of test that we're actually doing with this. Okay. Most of the stuff that we're going to do is the exact same as what we did with the two mean hypothesis tests. So meaning that the null and alternative, the null is going to be x bar 1 equal x bar 2, and then the alternative is either going to be x bar 1 greater than x bar 2, x bar 1 less than x bar 2, or x bar 1 not equal to x bar 2. At this point, we always want to define the groups, okay, just like we did with with the two mean tests that we looked at before. We're going to get only a few variables. The variables we need are going to be x bar 1, x bar 2. In other words, the mean of group 1. All right. So if I were to average the items from group 1, 10 plus 8 plus 9, that would be 27 out of 3, so the average would be 9 from that group. So that's what we're talking about with x bar 1. With x bar 2, we could do the same thing with group 2. We need n, which is going to be the number of paired samples. So in this case, n would be 3, and then we need an alpha level. Based on that, we're going to get our t critical. Now t critical is going to go back in a good way to alpha and degrees of freedom. Degrees of freedom is n minus 1. And just like we always do, if it's a two-tailed test, we have to remember to split alpha before getting t critical. Once we have that, then what we're going to do is we're going to do the computation, or we're going to set up the distribution. The distribution is the same as always with the t distribution. So you either have negative t, positive t, or alpha, and then you split t. We're going to have two things that we need to compute to be able to get the test value. To get the test value, first we're going to find this thing called SD bar. That actually stands for the standard deviation of the differences. All right, and different, when we say d is equal to a difference. So in other words, d1 would be 3 because the difference between 10 and 13 is 3. d sub 2 would be 1. d sub 3 would be 1. All right, sometimes d can be negative. All right. So that's what we mean by the differences. And then finally, we get a test value. Test value is computed by the difference in the sample means divided by SD bar divided by the square root of n. From there, we can go through and do the computation and then determine if we're going to reject or fail to reject the null. So let's jump into an example. So let's say there's a claims company, or a company claims that its 12-week program significantly reduces weight. The following 4 samples were taken showing the before and after weights of 4 randomly selected customers. Is there evidence to suggest that the average weight of the customers is significantly less than the average weight than when they began the 12-week program? We're going to test at the 1% significance level. We would assume that there's no difference in the averages before and after if there's truly no influence from exercise. However, we know that generally if you adhere to a weight loss program that you're probably going to lose weight, and we want to see if it's significant. We know that significantly less. All right, so we're going to say X bar 1 is less than X bar 2, and however, we're going to define the 2 groups. Now, we know that after somebody goes through the program, they should lose weight. So we're going to define the after group as group 1 and the before group as group 2. Now we're going to start getting some variables. We need an X bar 1, and X bar 1 is just going to be the sum of all of the after weights divided by 4. So that's going to be 183 plus 187 plus 161 plus 204, and we're going to divide all of that by 4 to get X bar 1. All right, so all we're doing is we're just taking the average of these 4 values. All right, and I'm going to type them in my calculator if you could do the same thing just to verify that you're able to compute. And I wind up with 183.75 X bar 2. When we compute that, what we're going to do is we are going to take the average of the before groups. So we're just going to add up those 4 numbers. We're going to divide by 4. So that's going to be 180 plus 195 plus 177 plus 221. We're going to divide that by 4. And I end up with 193.25. The number of samples n, there are 4 samples in this example. All right? So there are 1, 2, 3, 4 subjects. And then finally, the significance level is going to be 1%. It's not a two-tailed test, so we can immediately try to figure out T critical based on the fact that alpha is 0.01. Degrees of freedom are going to be 3 because that's n minus 1. So we're going to go into our T distribution. And I did not have mine pulled up. I apologize. One moment. And if you all can verify, at 1% significance and 3 degrees of freedom, 4.541 is T critical. Okay, so T critical is going to be 4.541. When we plot it on the distribution, because we have a less than problem, it's going to be a left tail test. So here's what our distribution is going to look like. Now we have a left tail test. So we have 4.541 negative. And remember, the range of values is negative infinity to positive infinity. And then 0 is going to bisect the distribution. Now we can finally go through and we're able to compute what the test value is. Since it's the first time we've done this, I'm going to copy and paste the 2 values that we need. So we need this SD bar and we need the test value T. Now, before we can get SD bar, we actually have to find the differences. All right, so what I'm going to do is I'm going to make a chart. Remember, we had the after and then we had the before weights. All right, so I'm just going to copy those down in a vertical fashion. and I might have to bounce back and forth. 183, 187, 161, and what was it, 208, 207, 204. And then we have 180 for the first before. So all I'm doing is I'm just copying it down from right here. 195, 177, 2921. I'm just going to do one more check just to make sure I copied those correctly. 95, 77, 21. Okay. Now we're going to find the difference. So the difference D is just going to be subtracting. So 183 minus 180 is 3. 187 minus 195 is negative 8. 161 minus 177, that's going to be negative 16. And then 204 minus 221 is negative 17. Finally, we're going to find D squared. Now D squared, we're going to square each of the numbers in the previous column. Remember, whenever we square a number, it becomes positive. So our numbers should be 9, 64, 256, and 289. Now, I'm not sure what happened up here, but it looks like that our formulas got a little bit messed up. That's okay. Maybe not. So I'll copy them back down. Not sure what happened there, but we can delete those, no big deal. So, all right. So now that we have those, last thing we're going to do is we're going to add these columns up. Right? And if we add the columns up, I'll just do this as quickly as I can. So the first one is negative 38. Okay, and this is the sum of D. Sum of D squared ends up being 618. So this is the sum of D squared. Okay. And we have two formulas. Okay, so let me copy those down again. We have SD bar, which is equal to the square root of the sum of D squared minus the sum of D quantity square over n divided by n minus 1. Now if we plug that into our formula, that's going to be the square root of 618 minus negative 38 squared divided by n, which is 4, divided by n minus 1, which is 3. As we've done a lot of times with standard deviations, it's probably best to compute the numerator independently first. So I'm going to punch that in my calculator, and all you're going to do is you're just going to literally type it in as 618 minus quantity negative 38 squared divided by 4 in your calculator. All right, so I'll type that in, and I end up with 257. So this ends up being the square root of 257 over 3. And if we approximate that, 9.256. Now that's the standard deviation. Okay. Unfortunately, that's not the answer to the question or the test value yet. Okay. So I'm going to make myself a little more space here. Right. To find the test value t, that's going to be the difference. So test value t is going to be the difference of the means. All right, things are disappearing. So I'm going to stop this video here, and then I'm going to finish up in another segment. I'm not sure what's happening.